Okay, here's another example of a double integral. So the question is, find the volume under the graph of f of x comma y equals to 1 minus x minus y in the first octant. You may never heard of this word called octant, but it's obvious what it means. See, in the plane, that you have the quadrant, right? Because the x and y axis, it divides the entire plane into 4 parts. So you have first quadrant, second quadrant, third quadrant, and fourth quadrant, right? In the same way, you have the octant. And the xy plane, yz plane, xz plane, those 3 planes will divide the entire space into 8 different regions, and those are called octants. And of course, the first octant means what? The place where all the x, y, and z coordinates are positive. That's the first octant. Okay? Now, then the obvious question that you can have is, what's the second octant? And the answer is, we don't have a definition for a second octant, so there is no agreement in what's the second octant. I guess there is an agreement for the 8th octant, which is the place where all the x and y and z coordinates are negative. But that's about it. Nobody talks about the second octant or third octant. It's useless, so people don't use it. Okay. So, the first octant is always the place where x, y, and z are positive. Okay. Now let's think about what the volume of this object is. And once again, I want to predict the answer before we actually do the computation, because that makes more. That gives us more confidence of what we're doing. Okay? All right, so let's try to draw the graph. The graph means you say z equal to fx comma y, and fx comma y is 1 minus x minus y. So let's think about this graph. All right, if I move this to the other side, I get x plus y plus z equal to 1. And for this one, I think it's better to use xy trace, yz trace, and zx trace to draw it. So first, xy trace. What's that? That's x plus y equal to 1. Is y equals to 1 minus x. So xy trace is like you have 1, and the slope is negative 1, so that's the graph. Now, on the first octant, first octant is where x and y are positive. You only have this portion. Okay? So that's the portion which belongs to the first octant. Okay? How about yz trace? In that case, you have to set x equal to 0. So you get z equal to 1 minus y. And that's like y and z, and it's the same kind of graph. It has the z-intercept 1, and the slope is negative 1, so the negative 1 slope is a 45-degree line that's going downwards. We all know that, right? And again, the one that belongs here belongs to the first octant. It is here. Okay? And the same thing for xz trace. Those. Now what? Can you imagine what kind of graph that is? So if you had maybe I want to say this is x and that's y and that's now the x y trace is like one here, and it's this triangle at the bottom, right? XY trace. XY trace. This is one that's one. It's a you draw a straight line connecting these two, and it's this triangle that we get. And then how about the YZ trace? YZ trace is, here's one. It's this part, right? And then XZ trace is here. So how many sides does this have? Four. What do you call such an object? It's basically like this. To say four, you use the word tetra. Yeah, tetrahedron. It's a tetrahedron. It's not a regular tetrahedron because not all the lengths are the same. To be more specific, this side is a right triangle, and this other side is also a right triangle. All right? All good? Right. Now let's try to find the volume. We actually talked about tetrahedron volume before, right? Tetrahedron volume is what? If you have the cube, what? 1/6 of the entire parallel pipe, right? It's 1/6 of the parallel pipe. And since these all sides are 1, if you complete it as a cube, it will be 1. So the volume will be 1/6. So we know that the volume will be 1/6. The volume. Now, we actually know how to calculate the volume using integrals because you learned such a thing in Calculus 2. If you worked really hard in Calculus 2, then you learned how to do this. So let me explain how that was done. So method 1, Calculus 2 style. In a single variable case, this is how you did it. First, you looked at this, the base of this tetrahedron, and you were thinking about this tetrahedron lying above this region, and what you did was you took either the cross-section in the parallel to the x-axis, or the cross-section that's parallel to the y-axis. Let's just pick the cross-section this way. Okay. Now here's a question. What's the equation of this line? What's the equation of this line? Y equals to 1 minus x. That was the equation that we were using. It's this one that we were looking at, right? Y equals 1 minus x. And then, if I had a random point x between 0 to 1, what's the height at that location? 1 minus x, right? So at any point x on this location, this length here is 1 minus x because that's what y is, right? Now, if you took a cross section at this point right here, what shape would you get? See, it's a tetrahedron over it. So if you cut it, you're going to get, somebody said it?
Trapezoid?
No. If you cut it like that, it'll be a triangle. Okay. What kind of triangle, though?
A right triangle?
It'll be a right triangle. See, if I take this, so this is a tetrahedron, and if I take this cross section here, maybe I should draw it bigger. So it's right angles here, right angles the opposite side, the base is also right angles. Okay? So it's supposed to be a cube, cut it in such a way so you get the tetrahedron. So if you took any location x and took this cross section, the shape that you're going to get is a right triangle. Okay? Not only that, it'll be an isosceles right triangle, okay? Meaning that if this length is 1 minus x, that we had, as we said, what's this length? 1 minus x. Okay? Agreed? And then, think about the area of this thing then. Usually you call this area of the cross section. What's the area then? How do you get the area of a right triangle? 1/2 base times height. 1 minus x times 1 minus x, so it's 1/2. 1 minus x squared. Okay? And then what do you do? To get the volume, what do? You do the integral of, so you say the volume is equals the integration of the cross-sectional area dx, where x goes from 0 to 1. Because that the minimum value of x is 0, maximum value of x is 1. And therefore you get integral from 0 to 1 of 1/2 1 minus x squared dx. And then you can actually do the integral from here. What's that? That's 0 to 1, 1/2. 1 minus x squared is 1 minus 2x plus x squared. If you multiply everything, right? You have to FOIL this out to get this. Hopefully, at this point in math, nobody questions why we have a negative 2x.
We can pull out the half, right?
Huh?
We can pull out the half.
You can pull out the half, thank you. And then we can integrate this, this, this. So 1 integrates to x, 2x integrates to x squared integrates to 1/3 x cubed. And you plug in 1 and 0. Okay. What's that? If I plug in 1, you get 1 minus 1, which is 0, then you get 1/3, right? And then when you plug in 0, everything is 0, so you get 0. So you get 1/2 times 1/3, which is 1/6, as we said before. Okay? So, and this is just purely calculus 2. You've done questions like this, maybe not many, but you were exposed to such a method in calculus 2 before. Okay? All right, now let's try to do this in calculus 3. Here's method 2, and eventually it'll turn out to be exactly same as that. Let's see, method 2. So in calculus 3, this is the way we're going to think. We're trying to integrate this multivariable function over the domain. So the base area is this, right? So we're still talking about this, right? This domain here. Over this, we have the function, and we are trying to multiply the function value times dx times dy, but this time I'm going to multiply dy times dx. It's the same thing, right? When it comes to actual calculation, they differ, because here we are integrating by y first and then x. If I could also have done it as dx times dy, then the calculation will be different, but at the end of the day, you're going to get the same answer. Okay? The reason I'm choosing dy times dx over dx times dy is because by doing this, I can actually compare what we're doing to what I did over here. Okay? If I do dx times dy, and it'll be a different computation than what I have here. Okay? So forgive me for writing dy dx, but at some point I'll also teach you how to convert between the two. Okay? So it's going to come later. For right now, just see how I'm doing this. Okay? So first, before I do any computation, you have to look at this and have some understanding of what this symbol means. Does that make sense? Does this make sense? Okay. The function value over some dx dy, right? So you get this piece of a volume, right? And you're adding all the volumes of these columns over this domain. Okay. So, and actually the heights change, right? So, why did I erase this? So, what's happening is over this domain, at each point I'm erecting this column, right? So over here it'll be taller. Over here it'll be smaller. And what I'm doing is I'm adding up all the volumes of these columns so that at the end of the day, I'm going to get the volume of the entire thing. Does that make sense? Yeah, that's what I'm trying to do. Good? All right. Now, so that's my first step. Now I have to insert concrete things, the actual functions. So here, this is 1 minus x minus y, that's easy. But to actually do the computation, I have to fill something in here and there, here and there. What do I put in? Well, the last one's easy. X varies from 0 to 1, so that's not a problem. But this one requires a little bit of thinking. Because if I just did 0 to 1, what does this mean? It's just the Cartesian product of two sets. So you get this square. And that's not what we want. We want this. We want only half of it. Okay? So how do I fill this in so that instead of getting the entire square, I only get this? Okay? Then you realize that what's happening is that the starting point is always 0, right? So you're trying to go that way, right? When y is changing, the y values are starting from here and then it's ending here, right? So starting from here and ending there. So they're always starting from 0, so that one is not a problem. 0 is not a problem. But what's the hard part is how do I make it stop at these points?
Would be 1 minus x.
Yes. 1 minus x is where you want the y to stop, because you want to stop at this curve. So really, here's how you're going to think. From now on, when you see this double integral, this is how you're going to think. This base here is really graph x equal to 0. What is x equal to 0 as a graph? It's a horizontal line, which is the x-axis, right? This one here is y equals to 1 minus x. No, sorry, it's wrong. Sorry. Y equal to 0. I'm sorry. So y equal to 0 is this x-axis, and y equals to 1 minus x is this line. And what you're saying is, I really want to start from this line here, and I want to end with y equal to 1 minus x. I start from this curve, I end at that curve. That way, I can make the integral to represent this triangle, not the entire square. So that's the main idea. Okay? Now, once you agree with this, now we're just going to compute. Okay? Let's try to compute. What's the integral of 1 by y? Y. What's the integral of x by y? Well, x is not changing with respect to y, so when you integrate x, you should think of x as a constant, right? So it's just like the opposite of partial derivatives. This is like partial integration. So if you integrate x by y, you get xy. Right? Because if you integrate 1, you get y, right? If you integrate y, you get okay. And then with this, what I have to do is I have to set y as 1 minus x, y as 0. I have to do this. Okay, that's what I have to plug in.
Y squared over 2.
Oh, thank you. This should be 1. Okay? So far, so good? All right. Now, pretty soon you're going to see that what we're doing is exactly the same as the Calc 2 one. Because, let's see. If I plug in 1 minus x, this is one I'm getting. 1 minus x goes into y. And 1 minus x goes into y. and minus 1/2, 1 minus x goes into y. And you're trying to integrate this by x, right? Let's calculate what this is. I should really erase this, but I want to save this computation to compare, so I don't have much room. Maybe I should just compute here, 0 to 1. So that's 1 minus x minus x squared, no, plus x squared. Is that right?
Yes.
Yeah, x times 1, x times x, right? And then what about this? Minus 1/2, 1 minus 2x plus x squared, dx, right? And now look, 1 minus 1/2, what's that? I have 1, I have 1/2. 1 minus 1/2 is 1/2. I have negative 2x, and 1/2 of 2x is just x, and it's a plus. So negative 2x plus x, what's that? Negative 2x plus x, what's that? Negative x, right? So it's negative x, okay? And then this is x squared, and I have negative 1/2 x squared. So I have x squared minus 1/2 x squared. What's that? 1/2 x squared. Isn't that the same as this one? Same exact thing, right? If you multiply 1/2, it's exactly the same thing. You see that? So after this, the computation is the same thing. It'll be something, something. It's exactly the same computation. You end up with 1/6. The same way. So, in a sense, you've learned something new. The new thing that you learned was how to put these limits, right? But in another sense, it's just a different way of looking at what you already knew in Calc 2. Now, in the next example, I'll try to completely forget about everything else and then start all over. And because now you have some feeling of what these double integrals will do, it will be easier for you to understand.